Hello everyone, this is Brock Skaggs and I'm going to make this video where I'll be working in Sage in order to plot the deflection of a given beam. And so I've got a picture of the beam right here. As you can see, it is simply supported, got a pin connection on the left hand side, a roller on the right hand side, and it is experiencing a uniformly distributed load, lowercase w there. And so just to give us some values here, let's say that the beam is 10 feet long between points A and B there. The lowercase w, the uniform distributed load, is 100 pounds per foot. Let's have it as A36 steel, so the modulus of elasticity, or Young's modulus, is 29 times 10 to the 6 psi. And let's say the beam's cross-section is a standard steel section, S4 by 7.7, which has a moment of inertia about 6.05 inches to the fourth about its horizontal centroidal axis there. And so with that, let's just jump right into solving the problem with Sage. And so the first thing I'm going to do is just create some variables to hold my known values here. And so example here, I know that the length is 10 feet, and then I'll just convert that to inches. That way it will be dimensionally correct when I go to have the length in inches and my E value, which is the Young's modulus or modulus of elasticity, times 10 to the 6, that'll be in psi. Also I, the moment of inertia, 6.05, there we are. And that's going to be in inches to the fourth there. Will also need to be there. And finally, the lowercase w, that was 100 pounds per foot. So divide it by 12 should get me to a unit of pounds per inch there. And so all I'm doing is basically taking all of the values that were from my problem statement, you can see in the lines commented above, and storing those into actual variables. And so one of the things you would have to do before you could actually get to solving the ODE would be to actually define the bending moment equation. And so that's what I'll do first. We'll say bending moment equation definition. And so here I'll just call it bending moment to store this expression inside of a variable, and that through some statics is negative w over 2 times x squared plus w times L divided by 2. Now let's group these all together, and that's multiplied by x. There we are. Shift enter there, and I can say something like show bending moment, just to check to make sure, yes, it has the values there. Here it's substituting the actual values for lowercase w and L in order to come up with those numerical values like negative 25 over 6 instead of negative w over 2. And so that's looking good. Don't really need that anymore. And so now the actual solving of the ODE. And so the ODE that I'm thinking of is that the second derivative of this curve, which characterizes the deflection of the beam at any given point, is equal to the bending moment expression, so m of x, divided by the product of the moment of inertia, I, times the modulus of elasticity, E there. And so I'm going to have something like y double primed. So the second derivative of this function is equal to m of x divided by e times I, where our m of x is this bending moment, and then e and I are just these constants up here. And so the first thing I'm going to do to actually get this going is I'm going to create a symbolic function. And so just like there, I'm saying y is equal to the symbolic function y as a function of x. And so this will help me to be able to say, hey, I want to take the derivative of it twice and write that in a differential equation. And so at this point, I'm going to say, well, we need to define the differential equation. And so that diff eq, if you will, is going to be equal, well, to the second derivative of y. So I'll say differentiate y with respect to x 2 times. And so that is the syntax. Diff is the function call. We pass in y, our formal function. And we're differentiating it with respect to x, and we're going to take 2 derivatives there. And so that is equal. Notice I'm using the double equals here, not the assignment equals. And we said that was the bending moment divided by e times I here. And just to check, let's just say show diff eq. We have a few issues here. I think we'll be okay. And we've got the second derivative of y, and here's our function there on the right hand side. And so I think we're in good shape, and we'll just go ahead and press forward now with trying to solve for the differential equation. And so I'll say solve ODE. And so the way we'll solve ODE is by using the DE solve. And so I'll just go ahead and show that. It's help menu here, and just type in DE solve question mark question mark. And so we should be able to see what we have to provide it here. And so just coming down here, here we're saying, hey, solve the differential equation for y. And so here it's a first derivative, the derivative of y with respect to x plus y minus 1, and solve that for y, and it's coming up with a solution. Also, you can see it works for boundary value problems, so boundary solutions here where we would pass in x naught and y of x naught, x1 and y of x1. And so this is the route we'll take to describe the actual conditions which go to the particular solution of our ODE. And so for us, it'll be saying something like at x equals 0, the deflection is 0, and at x equals L, the deflection is 0 as well. And you also might have a initial value problem, which is similar to right here. And so example here would be on something like a cantilever beam, where we'd know something like at the origin, at the fixed connection, the displacement would be 0, the deflection, as well as the slope there as well. And so those might be two different forms if you're starting to do this beam analysis here, depending if you had a cantilever beam and you knew just stuff at the fixed end, or if you've got a simple supported beam where I know the deflection at both ends there, at the pin connection as well as the roller on the right hand side. And so as usual, if you ever have any questions, you can just hit the function name, a couple question marks, shift enter to evaluate, and it does bring up for you the help information. And so using that, we'll say, let's calculate the deflection. Notice it's DE solve here. And so just hitting DES, I'll hit tab there in order to bring up my list. There's DE solve. Oops. There we go. And then inside of the argument, so what are we passing? Well, we're passing the differential equation, so diff EQ. What are we wanting to solve for is the next part. So we want to solve for y, comma, and now we want to express the conditions for our particular solution inside of square brackets here. And we said it was a boundary value type problem. And again, we know that because we basically have the origin here on the left-hand side right above point A. Or we got the positive x-axis going to the right, and so we know the deflection at point A is 0. The deflection at point B is also 0. So that's at x equals 0, we know that the deflection or the y function is 0. And then we know the deflection at x equals L is also 0. And so we just need to pass that information now into DE solve. And so 0, 0. First 0 here is at x equals 0. The y value is 0. And then at x equals L, which is the third character here, the y value is also 0. And so that should be able to help Sage figure out the exact function that we're looking for. And so when we're done, let's just say show the deflection. And so it crunches its numbers for a little bit, and there is the result there. And so let's test this a little bit. One thing we could say would be to look at specific points. And so let's do that. Deflection of beam at a specific point. And so to do that, we could use the print line. Say, okay, let's print deflection at x equals, say, the midpoint L over 2. Expect the maximum value to be there. I'll say plus string round, and we want deflection. Let's in parentheses x equals 0.25, not 0.25, 0.5 times L. And that just specifies the x value, and then we'll round that to 4 decimal places. I'll put a string here and say inches as well. And so what we're doing here is basically saying plug in the midpoint, x equals 0.5 times L, into deflection. This should return a number, and then we're rounding the number to 4 decimal places, and then we're converting that number to a string, is the last part here, in order to we can print it out to the text line here. I could just very quickly even then just copy and paste this and say, well, what's x equals L over 8? This would be 1.125, and get it there. We could do one more just to test the in condition. And so if I put in x equals L, I would expect the deflection to be 0. And so here, and there we go. And so it seems to be behaving just as expected here. And so again, all we're doing is basically passing in specific x values now into our deflection function and having it return the value, but we're doing a little bit of rounding in there and then casting it as a string. Another thing we could do is actually plot the deform shape of the beam. And so we'll do that next. Here we could just say something like plot the deflection, and it would be with respect to x from 0 to L. That's the entire length of the beam. And so there is the nice deflected shape of the beam itself there. You can see the max deflection occurring right at the midpoint, and we know that max deflection to be a little over 1/8 of an inch downward, 0.1282 from this line right here, line 35. And so this has been a fairly quick video where we've basically used SageMathCloud in order to examine the deflection of a given beam. And so again, just to recap what we've done, here in this chunk of code, we're basically just setting variables equal to the known values right from the problem statement. Line 20 here, we are defining the bending moment expression. And so this would have required a little bit of statics to be done outside of Sage in order to come up with that relationship. And lines 23 and 25, we're setting a function y, so we know that y is dependent on x, and then we're setting up our differential equation. We've got the second derivative of y is equal to the bending moment, so usually m of x divided by e times I. And then in line 27, we're actually calling DE solve in order to solve for the deflection solution. And so we're saying DE solve, passing in our diff EQ, that's right here, saying solve it for y, and then these characters inside of the square brackets are essentially describing the boundary conditions that we know that this deflection curve is going to have to obey. After we show it, just to make sure that we have a result, we're just querying the deflection at specific x values, and then finally we're plotting it down here. And so hopefully this quick video helps you work in Sage with using the DE solve command to solve ODEs, and specifically help you with looking at beam deflection. Thank you for watching the video.